Welcome back to Class 6. This is the second video. In the first video, we reviewed the relationships between stress and strain that we should have learned from mechanics and materials. Now I'm going to continue on with stuff that isn't in the book, but is very useful. So I decided to include it in the course. All right, so here's how the equations are related. If you know the stresses, you can find the strains. But in real life, we can't really measure stresses. We could maybe measure forces if we have some type of load block, but truth be told, we're actually measuring strains. But we can measure strains with a strain gauge, and we're going to deal with that. So I actually, at one point, when I'm teaching this class, actually wrote all of these out longhand, but I didn't see a tremendous benefit for doing that, of using the time to be able to write these things out. So I've included them in my notes. So when doing homework, you should download these notes right here to find these equations, right? So this is just the demonstration that we've inverted matrices in order to get a relationship and get down for the three-dimensional stress from the strains equations written out down below. All right, and so they're not intuitive, although look, we could tell right here that we have these strain, the shear versions of them. They do work out. They are easy enough. So because you can see with this over here in these matrices, there's a lot of zeros right here. So it's really only this top 3x3 that we really had to do a matrix inversion on in order to get this relationship right here, right? And the only thing that I would add to this, to these, is the case that we have probably most often is for biaxial strain, right? And so biaxial strain from stress looks like this right here. It's pretty intuitive. These, I've actually had a little bit of problems when looking through the results that I got from up above here in trying to reconcile the algebra, how this works out. But right here are the equations that I think that you should use when for doing problems right here. So, because most often the time we're dealing with biaxial stress conditions, because we're looking on the surface of something, and there can't be really stress on the surface of something in the out of plane direction unless you're dealing with, like, maybe you're underwater and you have something pressing on, or you're on the inside surface of a pressure vessel. Right? Remember, we covered pressure vessels in the previous two classes. One of the reasons why we're introducing this class now is because now that we have pressure vessels, we're able to have more complicated strain scenarios, because we can have biaxial stress in two different axes. All right, so here are the two equations we need to know about. So, and this is where we're going with the thing, and the reason why we would care is we have these things called strain gauges. And strain gauges, there's a picture of them, but maybe let's actually take a look at what a real one looks like. So I Googled it. Here you go. Here's a strain gauge. Here's an actual strain gauge, and maybe we could take a look at some more pictures. There's another cartoon of it, but you could see, in the, just looking at these little cartoons of them, you could kind of see that they have these. They're like little wires. And they're going back and forth. It's one single wire that's going back and forth and back and forth. And they use adhesive. Sometimes they even actually weld these things, but they use some type of epoxy quite often. And they don't do in the middle part right here, but they put this on there, and maybe they do it. Yeah, I think they actually do epoxy in the middle. But anyway, any deformation that takes place right here is really going to stretch the length of this wire, and the wire has a relationship between its resistance and the amount of deflection that it contains inside there. And you can calibrate this, and so if you measure the change change in resistance, it's proportional to the strain. So those strain gauges allow us to be able to measure the amount of strain. And that's it. The picture, they only showed it in one direction, which is nice. But if you want to find out the total strain that's going in all three directions or multiple directions, let's say, let me back up here. You'll see shortly that if you want to find what the stresses are due to the strains, right, you need to have three of these strain gauges arranged in something we call a rosette, right? And so you need three of them, and they don't necessarily have to be in the same configuration. I'm not even sure which one's the most common configuration. If you look up in a catalog for these, and one of the most common, you'll see the Omega catalog is a really common thing to like look up right here. Like you see right here is Omega. Here's a simple one. You might see that they come together as actually already placed together. Like here's one right here. Here's where you have three of them, and they have two of them are 90 degrees from each other, and one's at 45. But the basic idea is you need to have three strain gauges in order to get the total picture of what's happening in the plane. And we could go ahead and do a derivation and show you that the strains that you would get, this epsilon 1, epsilon 2, and epsilon 3, they represent the strains that each of the strain gauges would show. And this theta 1, theta 2, and theta 3 represent the angle that they are related to a particular axis. Most of the time, they're all going to be related to the first one. Whatever we decided was strain gauge number 1. We'll give that as the subscript. But you could kind of see here, these are arrangements from a textbook where they're showing you the different configurations. We just want something kind of that's sort of general so that we could take these readings that we're going to get, epsilon 1, epsilon 2, and epsilon 3, and what we want out of them are epsilon x, epsilon y, and gamma xy. So you can see there's three equations and three unknowns, all right? The knowns are going to be what we measure. So we're going to measure epsilon 1, epsilon 2, and epsilon 3, which are actually resistance changes that we've measured, and we've used the calibration from that resistance to be able to get what these strains are, right? And then we want to be able to solve and find epsilon x, epsilon y, and gamma xy. And so that's how we're actually going to be able, in the real world, to be able to find what we're going to measure is the best that we can with the instruments we have available, what the stress is right here. So I'm going to switch over to my document camera. So I'll go back over to my notes right here. And so now we're on page 4 of these notes, and like in the middle of the page. Let's see, you get this weird striping that takes place for the lights. And okay, so here are these equations that we described here, and so like here is an application, the strain gauges we see right here, and in this configuration right here, we're going to call this one is 1, is 2, and 3. And by the way, you'd have these leads that you'd solder onto here that would go to your instrumentation to pick this up. So looking at this right here, we're going to take the angle going this direction right there, right? So we can see that 1 is theta 1 is equal to 0 degrees. We could also see that theta 2 is equal to 90 degrees. And I think I made the other one 45 degrees, but you could actually argue that that's actually going to be 135 degrees. But I said in my notes here, and I think it's going to work out right, that theta 3 was 45 degrees right there, right? But I think from this rosette, it actually should be 135, right? Because it should be like that way from horizontal. But anyway, so let's put the zeros in for here. And note that there's a sine and a cosine here. And these are squared, but this is sine and cosine. And so we get 90, 90, 90, 90, and we get 45, 45, and 45, and 45. All right, so this one goes to 1, this goes to 0, and because this goes to 0, we could say that epsilon 1 is equal to epsilon x. Well, that's kind of obvious if this is the x direction right now. If whatever you're measuring here is definitely going to be that. So, duh. That goes to 0. This goes to 1. And this one goes to 0. So epsilon 2 is going to be equal to epsilon y. And so for the same reason, duh, no kidding. This one, however, is going to go to 0.707, but it's squared, so it ends up going to 1/2. This one also, 0.707 squared is going to be 1/2. And this guy right here is going to be 1/2, I believe, right? I had to be careful with the 135 right in there. Let me double check. Let me double check this because people have pointed out that I've made mistakes on this before. And I think I'm okay with this. Yeah, I'm pretty sure I'm okay. So this is the only more complicated one. This is epsilon 3. We get 1/2 epsilon x plus epsilon y plus gamma xy, right? So you see we have 1/2 on each of these, but now we want to solve for epsilon x, epsilon y, and gamma xy for here. Well, first off, duh, epsilon x is equal to 1. Epsilon y is equal to epsilon 2. But gamma xy, all right, and so what we do is we substitute in, right, we say that epsilon 3, 2 times epsilon 3 is going to be equal to epsilon x, plus epsilon y plus gamma xy. Therefore, gamma xy is going to be 2 epsilon 3 minus epsilon 1 minus epsilon 2. So that's what we really wanted, right? So what the advantage of this rosette is we're able, in this case right there, yeah, we're just measuring x and y, but we're able to get what gamma xy is. We're able to get what the shear stress is in this configuration. All right, so now I'm going to do some more examples and some the follow-on videos. But that was like the basics. We're going to go through the same type of thing for the examples. We'll see. So let's see. We'll record these other videos for that. So it's a 12-minute video. That's fair.